Hello, I'm Alexandros, and today I'm happy to present our work assessing vision quality in retinal prosthesis implantees through deep learning, current progress, and improvements by optimizing hardware design parameters in rehabilitation, a joint work with Nikos Melanitis and Konstantina Nikita. Our primary motivation stems from the ability of living organisms to understand visual stimuli. So, what is the problem? Unfortunately, more than 100 million people worldwide are dealing with irreversible vision loss due to the deterioration of photoreceptor cells. Promising a solution to this issue, retinal prosthesis uses electronic implants to visually assist patients by externally electrically stimulating the surviving cells, bypassing the regenerated ones. These devices consist of a camera to digitally capture the visual world, a processing unit to process the camera input, and an electrode array that stimulates the retinal neurons according to the processed camera input. The final part is the one we are interested about in this work. The main question was to determine the hardware design parameters that would impact the final visual quality the most. In order to do this, we needed to virtually evaluate the quality of the prosthetic vision from an implant, and as a bonus, we wanted to study how this visual quality changes over time due to rehabilitation. Hence, our goal is to evaluate implantees' prosthetic vision with the help of deep learning and to computationally simulate the rehabilitation process. Through this, we can eventually evaluate the resulting vision quality of retinal implants. The importance of this work is closely related with the reduction of the development cost of implants by easily evaluating the prosthetic vision long before the implant's trials period. In addition, we try to provide guidance for design engineers to better focus on the important parameters of the implant's electrode array. Lastly, with this work, we help to set the hardware implant requirements in order to provide adequate prosthetic vision on basic activities. One of the challenges with the evaluation of retinal implants is the distortions that occur during the stimulation of retinal cells. For example, let's imagine a 15 by 15 electrodes array like the one on the picture. Common sense dictates that the activation of one neuron would produce a light blob in the location of the stimulated electrode. However, it appears we have some spatial distortions due to the excitation of ganglion action pathways around the electrode that produce elongated blobs. Extending this paradigm, by activating a group of electrodes in a line, instead of a line, we get a distorted output. Notice how the elongated visual perceptions follow the lines of the ganglion action pathways in the central image. The idea of using deep convolutional neural networks to model humans' classification ability, or HCA for short, stems from their biological inspiration. The original work of Hubel and Wiesel, where they studied the architecture and hierarchy of organic cells in the visual cortex, inspired the first biomimetic visual computational models, which in turn eventually evolved to the current convolutional neural networks, or CNNs for short. Another bonus is that deep learning models are, as the name implies, trainable, enabling us to simulate the rehabilitation process through training. Moreover, studies show that higher level of visual distortions causes both CNNs and humans to smoothly decrease classification rates, suggesting high correlation between their visual understanding on distorted images like the ones coming from retinal implants. Finally, CNNs are the state of the art for computer vision understanding. Also, we use transfer learning to train the model on our data. The idea is to use knowledge gained from larger datasets like ImageNet to learn a new task on a smaller dataset like ours by only training the last part of the model. This leads to richer image vectors and also greatly mimics the human behavior of adapting knowledge from one task to another one, and it enables us to simulate the self-learning that occurs on the rehabilitation period. And now to the actual method overview. We divide this into two parts: the image preprocessing and the modeling of the human's classification ability with convolutional neural network. We use the MNIST and the Cypher10 datasets to represent both an easy and a more difficult visual task regarding digit and object recognition respectively. We simulate prosthetic vision in square, fixed area retinal implants of various parameters in a subset of the MNIST and the Cypher10 datasets. Thus, we generate our new implant datasets, one for MList and one for Cypher10, for each of the implants. In addition, we model the HCA with a CNN, which we train on the initial non-prosthetic vision datasets. This represents the ability of a human to recognize digits and objects. This model is then evaluated on the implant datasets to show the ability of the implantee to recognize the same objects. Lastly, we apply the transfer learning paradigm to the new datasets for different training durations to represent the short and long-term rehabilitation periods. Regarding the initial training of the HCA model, we start with two ResNet34 models, which are a type of convolutional neural network pre-trained on ImageNet, and we train them on digit and object recognition respectively using transfer learning. Then, to generate the implants datasets, we use two different simulation models, the scoreboard model and the action map model, which describe the two types of expected outputs we saw earlier. For implants, we create and simulate 182 different implant configurations of constant area, but with varying electrodes number and size as displayed on the slide. In addition, to evaluate the current progress of retinal prostheses, we also simulate the commercially available Argus 2 retinal implant. So, the process of creating the implant datasets is as follows. First, we tightly crop around the initial dataset's images if needed, and we subsample to the size of the implant. Then, we stimulate the corresponding electrodes on the array. Lastly, we simulate the prosthetic vision, we crop around the stimulated area, and we add padding if needed to match the input dataset style. After creating the implant datasets, we evaluate the HCA models for digit and object recognition to each of them. This represents the zero rehabilitation time period. Next, we train each of the HCA models to each dataset using the transfer learning paradigm for one epoch, and we evaluate again. This evaluation represents the short rehabilitation period. Lastly, we continue training the same way for another 19 epochs, and we evaluate one last time. This evaluation represents the long rehabilitation period, months to years. Results show that most of the times, the scoreboard model is a good approximation of the action map model, especially considering the relatively minimal computational resources it needs. Much more importantly, the electrode size seems to have minimal, if any, impact on the prosthetic vision. At most 8% difference between the best and worst configuration, which leads us to believe that designers should only consider the electrode size as a way to pack more electrodes on the same area. Lastly, from the final accuracy scores, we can point out that although in the easier task of digit recognition, 80 or more electrodes results in a very good vision quality, for the more complex task of object recognition, more than 350 electrodes are needed to provide adequate prosthetic vision. As for the Argus 2 implant results, the low electrode resolution cannot capture the needed visual information for more complex visual tasks. Still, for the simple task of digit recognition, we get relatively good results. More importantly, though, our digit recognition results closely match the results from actual experimental data for the slightly more difficult task of letter recognition, as shown on the right image of the slide. Here, we visualize the prosthetic vision for digits as well as objects for different sizes of square implants. On this example of digits, pay close attention as the electrodes reach the number of 81, where we can quite clearly make out the digits in question. In this example of objects, pay close attention as the electrodes reach the number of 361, where we can quite clearly make out the objects in question. In future work, larger datasets with more object classes like CIFAR 100 and ImageNet will be examined, as well as datasets with more complex tasks like the COCO dataset used for object detection that represent more real-world objectives. Moreover, investigating the impact of the shape and area covered by retinal implants is of great importance to attain a comprehensive overview of all design parameters that may influence prosthetic vision. Lastly, concerning the enormous computational resources needed to simulate even 6,000 images for 183 implants using the ActionMap model, we want to explore GPU acceleration that would enable the easy investigation of distortions caused by ganglion axonal excitation in prosthetic vision. Thank you very much for your attention.